corrective action, resources, case study, and discussion on remedial design, characterization, and in-situ remedial methods, is the third webinar in a four-part series NUIPIC is providing that builds off of the themes planned for the now postponed National Tanks Conference, which was rescheduled for September of 2021. Please be on the lookout for future announcements related to the webinar series and the 2021 National Tanks Conference. For today's session, attendees will learn how the Interstate Technology and Regulatory Council's web-based resources can be accessed and used in the cleanup of lust sites, particularly for sites employing in-situ remediation and injection. We will discuss the remediation of a lust site in Kentucky that presents unique considerations related to the use of surface geophysical methods prior to invasive bedrock investigation and remediation. Finally, we will discuss the value of the remedial design characterization, or RDC, and advancements made in-situ injection techniques for remediation. As mentioned, the webinar wrap-up will provide perspectives from the panel on the investigation and remediation of lust sites via audience Q&A. In the handout section of the GoToWebinar panel, you'll find a copy of the slides for today's presentation. NUIPIC will be posting the slides and the webinar recording to our online archive for future use. And after the completion of today's webinar, you'll be automatically prompted to an evaluation form. Thank you in advance for providing your feedback. And an electronic certificate of attendance will be emailed to the address used to register for this webinar. Please note that today's presentation has not been evaluated to meet any continuing education requirements. So I'd like to go ahead, and it's my pleasure to introduce today's awesome speakers. First, Chris McCandless has worked for the Virginia Department of Environmental Quality in Woodbridge, Virginia since 2015. As an environmental geologist in the Petroleum Storage Tank Remediation Division, he manages the characterization and remediation of numerous leaking petroleum storage tank sites, as well as assists the land protection program with chlorinated solvent sites. Chris has spent most of his career as a project manager and hydrogeologist in the environmental consulting field. While reaping the benefits of many ITRC webinars during his consulting career, Chris joined ITRC's characterization and remediation of fractured bedrock team soon after employment with DEQ. Chris was an active leader in preparing and now introduces the web-based training for ITRC's latest document, Optimization of In-Situ Remediation, which was published on the ITRC website in February of 2020. Chris earned his Bachelor of Science degree in geology from George Mason University and is a certified professional geologist in Virginia. Welcome, Chris. Up next is Vicki Voisard, is a registered geologist with the Kentucky Division of Waste Management's Underground Storage Tank Branch. She is a graduate of Ball State University, where she earned her Bachelor of Science in Geology and her Master of Science in Micropaleontology. Prior to joining the Division of Waste Management, she worked in the private sector with multiple companies, during which time she was recognized for her work in Indiana and Ohio. In 2003, she joined the Division of Waste Management as a reviewer overseeing activities at the Paducah Gaseous Diffusion Plant, a U.S. Department of Energy NPL site located in western Kentucky. In 2018, Vicki transferred to the Underground Storage Tank Branch as a reviewer, where she currently directs and oversees remedial activities at 51 lust sites. She's responsible for strategies and directives that involve planning, implementing, and evaluating contractor relations and job site policies, programs, and practices. We're happy to have Vicki here. And finally, Bill Brab is a senior remediation geologist at AST Environmental, Inc., with over 18 years of experience in environmental geology and remediation. He started working for AST in 2011 and has developed AST to become a leading in-situ technology company, providing a unique injection approach involving high-resolution sampling, detailed conceptual site models, intricate designs, and injection techniques. Mr. Brab graduated from the University of Kentucky in 2001 with a Bachelor of Science in Geology and holds professional geologist licenses in Kentucky, Tennessee, and Alabama. We're so happy to have all three of our awesome speakers here today with us. And with that, I'd like to begin with today's first speaker. I'm happy to introduce Chris McCandless with Virginia DEQ.
Thank you, Drew. Hold on a sec. Do I have screen? There we go. Everybody seeing the ITRC screen? Drew?
We sure do. Take it away, Chris.
Okay. Yep. All right, good. Well, while we'd like to be giving this in person at the National Tanks Conference, Vicki, Bill, and I are happy to share this presentation with you by this webinar. So thank you, Drew, and thank you, NUIPEG, for putting this on at this time. As Drew told you at the beginning, ITRC stands for the Interstate Technology and Regulatory Council. What is ITRC? Well, it is a state-led coalition working to advance the use of innovative environmental technologies and approaches to translate good science into better decision-making. The contributors to ITRC largely come from the private sector and from state governments, with the Department of Defense, Department of Energy, and Environmental Protection Agency and academia lending their expertise. As he told you, having consulted on the private sector side, having taken the ITRC webinars, and now being a state regulator, I can say with confidence ITRC is a great vehicle for generating thorough and modern guidance, uniting state regulators with the private sector to promote innovative technologies and to train the entire environmental community. This guidance and all of the webinars are free for anyone to use on the internet from the links given in this presentation. If you want to contribute to the articles, you are encouraged to do so as a state regulator. For you, it is free. But if you or your company has to join ITRC if you're in the private sector. Do we have any state regulators tuned in today? Okay, this slide is going to be my presentation guide. ITRC's internet-based documents and training used for leaking underground storage tank sites. So we're going to use about 3 of these to get into to apply to Bill and Vicki's sites and show you how to use the characterization and remediation of fractured rock, which was published on the web in December 2017. And then one of our newest ones is implementing advanced site characterization tools, published on the web in late December 2019. And then as we shortened it up to in-situ remediation, that was the document that I just had a big hand in helping out with, documenting and writing, is the optimizing injection strategies and in-situ remediation performance, published in February of this year. And then the other one that's going to be helpful for you is TPH risk evaluation at petroleum contaminated sites, published in November of 2018. As you read in the abstract for this webinar, our next 2 speakers will be discussing the need for accurately placing monitoring wells in the karst terrain and understanding the fracture and void network so as to effectively inject amendments to remediate contaminants in this geology. Vicki will be discussing her case study for the investigation of a Lusk site, and Bill will be discussing the importance of conceptual site model and remedial design characterization for the appropriate methods of injection and amendments selected for in-situ remediation. Okay, how important is the CSM? It is truly critical to every project that we understand the subsurface components, structure, flow pathways, geochemistry, and properties of the contaminants and their phases as best we can to build this foundation for cost-effective and successful remediation or installing replacement wells. I cannot emphasize this enough. The CSM is a key component within scores of ITRC documents produced in the last decade, and as you'll see borne out in this webinar today. So let's begin with ITRC's characterization and remediation of fractured rock that was published in 2018. We will start with this one because it best demonstrates why the CSM is so important. For most environmental scientists, including geologists and hydrogeologists, attempting to remediate contaminants in fractured rock is complex. Why? Because of the black box trance. The textbooks on groundwater principles teach us mainly about homogeneous and isotropic conditions, and it's the complete opposite when it comes to fractured rock, isn't it? So the fractured rock document is best summarized by this double-sided pyramid that you see in the upper left-hand corner of this slide. The fact that rock sites are complex is the tip of what they've described as an expanding pyramid of uncertainty and costs. There is uncertainty in the CSM. We are unfamiliar with the tools used, or we are not using them efficiently. And this all leads to ineffective remedial design and increased costs. Do you see that the authors chose to make the foot of this pyramid red? Red means stop. Stop this old line of thinking. The fractured rock guidance focuses on flipping this pyramid of uncertainty and costs on its head. This guidance provides the science to understand fractured rock characteristics, develop a conceptual site model using the appropriate tool, hint, the tools table, to develop and refine and optimize the CSM, which, as you can see, leads to remedial action goals that can be met in a cost-effective way. So to build the CSM, we need to look at three elements: geology, hydrology, and chemistry. So geology, we're talking about the physical characteristics, the type of bedrock, and the physiographic province of the site. Now, this is hydrology, not hydrogeology, because we are discussing water and contaminant flow characteristics through the fractures and in the matrix. And then chemistry is the chemical characteristics of the contaminant. The guidance introduces the parameters necessary for developing a fractured rock CSM and stresses the need for an experienced multidisciplinary team. As we aim to understand our Lust site or project better, I believe in doing some desktop research on our computers, checking on regional and local geologic maps. If you can readily find LiDAR or use it for regional trends, then zoom in and use aerial photography to verify those trends using fracture trace analysis. If you have outcrops at your site, look for fracture sets, for bedding planes and foliation. Look for published geologic 7.5-minute quad maps. Find those foliation markers like these on this Catoctin greenstone. And these, because as we know in the East Coast, so many of our outcrops are shrouded in vegetation. And if you're fortunate enough to have a highway or railroad cut near your site, size it up. Look for repeatability in the fractures. Get your Brunton compass out and measure that strike and dip data. Plug it into StereoNet and ROSE diagram software. I can tell you from experience, mapping the geology of a site allowed me to understand why DNAPLs, or sinkers, perk and dry cleaning solvents and that kind of thing, were on one portion of a bedrock site and their vapor phase was on the other. Again, with hydrology, we are looking at flow of groundwater, LNAPL, DNAPL, and other contaminants that might have leaked from a UST or some other source. While we gather this data about the site, let us remember the 9 bedrock properties controlling groundwater flow through fractured rock. To demonstrate these concepts, here are some photos that I took in the Valley and Ridge province of Virginia, probably a sandstone or a limestone there that is shown on this outcrop. Aperture is the opening size of the fracture or bedding plane. And while that wetness leaking out from that fracture in the bottom picture is most likely water, at your site it could be free phase or dissolved phase hydrocarbons. or chlorinated solvents. Okay, now this is the tool table from the fractured rock document, which was produced between 2015 and 2018. Note the different tools on the rows that are linked to various portions of the documents. These are all hot links because they're underlined in blue like that. Now we're going to see, I point this out because we're going to see how ITRC has made this tool table even more applicable and interactive in the advanced site characterization document. So this ends my discussion of the fractured rock document. So please head over to the ITRC website, download that document, and consider attending the next webinar, which is on December 10th. And you can find that all at the ITRC main page, which is included in this handout, I believe. Okay. My colleague at DEQ, right in my same office, Alex Wardle, was one of the team leaders to create this document, along with Ed Winter from guess where? From Kentucky. ITRC's Advanced Site Characterization Tools. This is the home page, and this icon bar is anchored at the top of every successive page that you open up, except for tables in the appendices, which open in their own windows. I'm going to show you what most of the icons do. So let's start with ACT's selection tool on the left, and we're going to see that it opens a separate spreadsheet. Do you see the boxes in upper left corner? Data needed, subsurface surface, data collection, data quality. It might be a little poor quality, but I'm sorry. This is a copy from the actual spreadsheet that opens up when you pull on that icon. So as you can see, data needed, subsurface, you have these different characteristics or parameters that they use to filter out which tools to use. Okay, so now watch when I select geology in data needed and consolidated bedrock in surface and subsurface, leaving all in data collection, meaning leaving that parameter open to give it to me all. And we press search, and voila, I get a filtered list of tools that now have all become hot links to their own content within the document, and include specific case studies where they have been used. You see the case studies here: cone penetrometer, electrical conductivity, borehole geophysics. Pretty cool, pretty cool. So here you get the parameters that are summarized above here. Now, clicking on the summary tables brings up this sort of abbreviated table of contents. Direct sensing in section 3 talks about tools such as MIP, LIF, and flutes, membrane interface probe, laser-induced fluorescence, and the flute diagrams for interval sampling in a borehole. Section 4 is borehole geophysics, which I'll cover shortly. Section 5 is on surface geophysics, and then remote sensing in section 6 covers aerial photography and LiDAR, etc. Okay, so now let's select tool descriptions in orange here, and because Vicki's going to be talking about surface geophysics, let's select this one. Now, what we notice in surface geophysics in section 5 is the subheadings are the same for each tool. So it includes use, data collection, design, data processing, quality control, limitations, costs, and the case studies that were used. This is the section of surface geophysics dedicated to electrical resistivity. 3D ER is shown in the cutaway block right here, but two-dimensional is the norm and the one Vicki used for her project. Here is what ER data looks like in the profile from two 500-foot lines that were performed in the Cambrian Catoctin greenstone outside of Leesburg, Virginia. This is on the east flank of the Blue Ridge Anticlinorium in Northern Virginia. This was a project that I had as consultant, wherein the residents' heating oil tank leaked and impacted their supply well, and we were tasked with finding the location for a replacement well. Do you recall that 7.5-minute quadrilateral map shown earlier? This was that site, and this was the successful find of groundwater at about 80 feet. Section 5.3 discusses GPR, ground penetrating radar, and shows some examples of the instruments used and how the data is presented. The radar sensing unit is coursed along the ground surface on a cart with a monitoring positioned near the handle. Kind of looks like a lawnmower, doesn't it? But gathering GPR data and used to find tanks and buried objects like that. Vicki's project used seismic refraction, which is used largely to determine depth to bedrock and is shown in this diagram. As she is going to demonstrate, their project needed to ascertain depth to bedrock so they knew where to set surface casing for eventual use of downhole geophysical tools. Direct sensing tools are in section 3. Here are 2 examples. Ever since learning of it a decade ago, I love using optical televiewer in an open bedrock borehole or supply well because it captures a 360-degree view of that borehole. Yes, it does have a sensor as to what is due north, so it knows the position of itself in the hole, and it can generate these logs that you see to the right. So you can interpret these sinusoidal waves as basically as the fracture embedding planes. That's what these tadpole plots are showing here. This is 0 to 90, and this is showing you either open fractures or bedding, banding, and foliation in the blue planes. So anyway, you can summarize this data, and this helps interpret the dip and dip direction that these are taken into actual strike and dips that you can plot in the rows and StereoNet diagrams. It's such a useful tool. And you'll see examples of this in both Vicki's and Bill's presentations. This is an example of integrated boring log showing the optical televiewer and the acoustic televiewer here. Natural gamma, caliper, fluid conductivity, heat pulse flow, which allows for constructing the monitoring well with these discrete sampling intervals. Now, Bill is going to get into this in much greater detail, so I won't labor this here. Finally, one of the last icons in this toolbar is for the training videos for the advanced site characterization tools. As they said, they wanted to put these videos within their document versus doing the webinars that we have for the other ITRC documents. Our third document is ITRC's Optimizing Injection Strategies and In-Situ Remediation Performance. Boy, about halfway through on working this, we came up with that refined title. It had all kinds, but it's certainly a mouthful. This document was started in 2018 by team leaders Dave Shear from Minnesota, Michael Smith from Vermont, and Janet Waldron from Massachusetts. It was the first ITRC document that I really participated in fully. From my experience on other ITRC webinars, I was able to help and create the webinar for this document and have already presented the introduction and wrap-up for 2 webinars this year. Our next one is coming up on December 1st. The target audience for this document is a practitioner or consultant who is either just about to start an in-situ remediation project or for that remediation site where a problem has occurred. Perhaps you're having initial success, but progress has stalled. Perhaps you've pushed the contaminant mass towards a sensitive receptor. Are you experiencing insufficient amendment distribution and contact at your site? Bill is going to cover this issue. Is your amendment daylighting, or are you using the vendor's dosing default values instead of data from your CSM? Perhaps you've written a good CSM, feel pretty confident about the remedy selection, but want to make sure there are no data gaps, or that your amendments will work with the selected delivery method. This document's purpose is to set you straight, give you solutions to optimize remediation performance. It is also written for the state regulators to identify potential shortcomings in remediation plans and to ask specific questions of the consultants and responsible parties. Now, we did not write this document as Remediation 101. You need to be familiar with the principles of in-situ remediation and preparation of a CSM. What is optimization? Optimization is the effort at any cleanup phase to identify and implement actions that improve effectiveness and cost efficiency of that phase. Now, you've heard us talking about optimizing the CSM, getting it right. This is what our aim is. Optimizing in-situ remediation is the management of risks and uncertainties through sound science. That was the definition of ITRC, wasn't it? The purpose, sound science and engineering during different stages of in-situ remedy planning and implementation. So, with that targeted audience in mind, we made this document more as a toolbox than one to be read cover to cover. There are numerous tables and links and 2 sets of fact sheets covering amendments and delivery methods. The sections within the guidance are laid out on the left side, and the tools for optimization are laid out on the right side of this toolbox slide here. As we better develop this guidance document, we discovered that optimization was the outcome of better characterizing our subsurface conditions. As I said before, improving the CSM, performing bench tests and pilot studies, making mistakes and then going back to an earlier step, i.e. the double-headed arrows. We realized that the most flexible approach had to be iterative. That iterative approach, the CSM, lets the CSM become adaptable to new technologies and new contaminants. This slide introduces the 3 major elements of our key graphic on the left, which correspond to the sections of the document. So remedial design characterization is section 2. What we call the design wheel with the 3 segments of amendment, dose, and delivery is covered in section 3. And then section 4 covers implementation, monitoring, and interpretation. The team further augmented the key graphic with what we call the optimization staircase, where in the process of implementing, monitoring, and optimizing, which are the small ovals that you see in these 3 pieces of the staircase, takes place during bench test and pilot test phase of the design phase here, and again during the actual full-scale implementation. Okay, so RDC is discussed in the first section of the document, and we can see its elements are the same as we saw in the fractured rock puzzle pieces, right? Now we're going to add in microbiology for the bioremediation aspect of remediation. So, most of the content of the RDC section of this document is contained in this very, very comprehensive Table 2.2. This table is long and meant to be scrolled on your computer, so I'm not going to show you portions of it. I'm just going to show you a portion of it for these fixed slides, but vertically it is separated into the 4 categories of the previous slide: physical properties, flow properties, aqueous geochemistry, microbiology, and then a 5th one is degradation potential. And the column headings include in situ approach, either that being abiotic or biotic, and the remediation phase or step that you're in. Are we doing screening? Are we in the middle of remedial design? Or are we already into performance monitoring? We nicknamed this the hover table because a detailed description of each parameter is given when you hover your mouse over the word or phrase. So when you hover provenance and mineralogy, up pops this to be helpful to see if you're in the right thing. And then this is flow path properties. So we're talking about anisotropy. And there's the definition. And for aqueous geochemistry, a huge discussion about sulfate. This is a short snapshot of the commonly encountered issues associated with remedial design characterization. Please don't try to read this. We have two other tables in Appendix B, commonly encountered issues with amendment, dose, and delivery, and commonly encountered issues with field implementation. I tell participants in our internet-based training webinars to use this as their personalized table of contents or troubleshooting guide, as it lists several scenarios and then offers links within the document and links to other ITRC documents to help lead you. You see how this is really a great toolbox? So many links. And that's why so many of the latest ITRC documents are all web-based, so that you can link and have the power of the web to go have all these resources at your fingertips. Delivery methods, table 3.4, helps the user determine which emplacement method of the 7 given up here is best based on the geology of your site. So D1 through D7 are hot links that take you right to the delivery fact sheets. And this is the page of those fact sheets. You can see that every one is a link. So, and every delivery method has a standardized set of subheadings: types of equipment, types of delivery, advantages, and limitations. For example, Bill is going to talk about direct push methods. He's going to talk about injection through boreholes and wells, and permeable reactive barrier construction. And linked throughout this document are the amendment fact sheets in Appendix A. Again, for the optimization of your existing remediation strategy, or one that you're about to implement, please use this document like a toolbox. Make sure your CSM is complete by referring to Table 2.2. Dive into the fact sheets and click on the hot links. Okay, ITRC's TPH risk evaluation at petroleum contaminated sites was designed to help evaluate and select advanced site characterization to support what? Here we go again, the conceptual site model. It's also meant to give the regulatory framework for TPH risk, provide TPH fundamentals, and assess human health and ecological risk using risk calculators, special considerations, and case studies. And again, here is the link to that document. So, in conclusion, I hope that you will now turn to these powerful tools for your simple and complex subsurface remediation projects: characterization and remediation of fractured rock, implementing advanced site characterization tools, and optimizing in-situ remediation. And with that, I hand it back to you, Drew.
All right, excellent. Thank you so much, Chris. Chris McCandless with Virginia DEQ. If you all attendees, if you do have questions for Chris, please, like we discussed, submit them via that questions panel, rather the questions feature on your control panel, and we'll work to get to those questions. I already got a couple good ones in. Work to get those questions put to the field, put to Chris or the panel later for Q&A. Thanks again, Chris. Next up, I'm pleased to introduce Vicki Voisard with Kentucky DEP.
Good afternoon. And as he said, I'm Vicki Voisard, and I'm going to present one of my case studies. And this happened to be one of the first sites that I was assigned to when I came over to the underground storage tank branch here at the state of Kentucky. Mine is a case study that happened in Boyle County, Kentucky, and that would be, if you're not real familiar with the state of Kentucky, it would be to the west of Lexington, Kentucky, and kind of a southeast direction from Louisville. So kind of a center of the state. And in this area, this was Maggie's Market, and this was the site that I had. And in the state of Kentucky, we have an awful lot of sites that have karsts located nearby, creeks, and springs, and this particular site had all three. We have the building here, which was a mom and pop gas station, grocery store. The tanks were right in front of the building along the road, and at one time, there was a domestic use well right here. People actually just drove up and filled up their water bottles. It had been properly abandoned before I took over the site, so that was one thing we didn't have to worry about, was a domestic use well. But we did have a creek running back behind, and on that creek is Mitchell Springs. And there were some karst features to the east of this site. So a little bit on the site history. On March 20th, 2014, two USTs were removed at this site, and it was noted that there was a visible soil staining on the pit walls and notable petroleum odor. The depth of the pit was 5.5 feet, and bedrock was encountered at 3 feet. So that told us that they hammered through bedrock for 2.5 feet, so they were able to set the tanks down below surface level. So in August of 2012, there were 12 soil borings were advanced to refusal, which the top of the bedrock, and those soil borings ranged from 3.7 to 6 feet below ground surface. So we did not have a lot of consolidated material above the bedrock. So in February of 2018, it was determined that data gaps related to the subsurface conditions at the site needed to be identified. So it was decided a geophysical investigation was needed to place the bedrock wells. The site geology was unconsolidated material beneath the site is predominantly a clay, silty soil. And the first bedrock unit to be encountered is the Middle Devonian Age New Albany Shale, which is underlined by the Boyle Formation. And the Boyle Formation is described as a dolomite, conglomerate, dolomitic limestone, and limestone. The limestone in the areas where we do have a lot of our karst features, so that's why we weren't surprised that there were karst features to the east of the site. And again, here's the location, pretty much where the crossroads met. Now, why did I end up choosing surface and borehole geophysics? There were several considerations when making this decision for a path forward on how to get this site cleaned up. First thing was the size of the lot. I just did not have a lot of room to poke a lot of holes. So whatever we were going to do to find the contamination really had to be thought out. The next was the New Albany Shale. It can be pinched out and it can go into 20-foot sections. It really varies from just, and we'll see from one side of this lot to the other, the thickness and the variability in that. And then the next was, how deep then are we going to find the limestone dolomite contact? And then the fourth major concern of mine was Mitchell Spring, which was to the north. We were not sure which way groundwater flow was. We had sampled several occasions the spring, and luckily never found anything in the groundwater that came out of the spring, but it still was a real concern. This is also, even though it's on private land, this is a public spring. This little area was one, and it's still known as Mitchellsburg. It was named after the founder, Mr. Mitchell, and he named this spring, and it was always deeded, even if the land was privately owned around it, that this would always be a public spring. So that was a major concern to me, knowing that people have access to that spring. So using the geophysics, the surface geophysics, we would be able to determine the best locations for 5 bedrock monitoring wells. And with the borehole geophysics, we would be able to properly screen the wells at the appropriate depths. So first was surface geophysics. And we went with 4 technologies on the surface geophysics and the instruments we were going to use in order to determine buried items. And the terrain conductivity with localized ground penetrating radar, the GPR, and that's one that a lot of people are familiar with, that they'll see out on a site, and it's back and forth on a grid. And then one that I had not seen before that we used on, that the company used on the site, was the CDM Explorer, and it's a handheld digital multi-antenna sensor, and it is very useful for positively identifying and documenting utilities, potential USTs, trenches, pits, voids, other structures, metallic or otherwise, that are within its limits of penetration. So it's also done in a grid, and he's got a handheld computer, and he's watching his path that he's going to go back and forth on. With the GPR and the lines, there were 3. There's the second one and the third line. These are profile lines, and when the readouts and the data comes to you, you're able to detect line 1. We knew at some time years past there had been a railroad line that ran through in the area, and we weren't real sure exactly what could possibly have been buried still back in there. This property slopes and really drops off as it goes into that creek area further to the north. But we were able to see here very clearly from the refraction back off the former railroad features that had been left. So there was debris buried down into that area through here. Line number 2, we were right in this section, able to see that possible utilities or some other type of buried metal objects were down in this area. And then over here, this was probably the heating oil tank that had operated when the business was operational. And then line number 3, which I thought gave a great view of the tank pit. So it showed how the radar penetrates down through the unconsolidated, the fill that was put into the pit, and then comes back up, and it gives a real good picture. And that was right in front of the doors of this building. So we had an idea of some things we were seeing down to 7 feet. So that was a big help on that. The third surface geophysics that we used was seismic refraction profiling, and there's also seismic reflection profiling. And the difference between those and why we went with refraction was refraction is for shallower events. The seismic reflection is generally applicable to depths greater than 80 to 100 feet. And we did not need anything at those depths. So in order to determine the geologic layers, a seismic line with geophones, and those were 3-inch spacing, and this is a 12-pound sledgehammer, and he used a metal plate, and you can see that they had marked the areas before they started with spray paint, so he knew where to put the plates at. And once he would hit the metal plate, that sends a shock wave down, and then it refracts along the boundaries between the geologic layers, and it returns up to the surface. So it would give us some good depths of the bedrock that we needed to bore down into. And then, of course, everything is, the lines are connected to the computer, and they ran 4 lines. So we had 4 profile lines from the refraction profiling. And the fourth one we did was the 2-dimensional resistivity, and that was also done with geophones and the lines, and these were spaced 3 feet apart, and you can see they did the 4 lines. This one ran east to west, and then there was the north to south, and then also in front, this is the south end of the property, and that ran from west to east. And what that was going to tell us is that fine-grained sediments, particularly clay-rich sediments, which shale is a mud clay consistency, that the clay-rich sediments such as glacial till are excellent conductors of electricity, while coarser grained sands and gravels are much more resistive. Carbonate rocks such as limestone and dolomite and sandstone are very electrically resistive when they are unfractured. So this was going to give us this, we'll be able to see it in the boring logs. There'll be a slide coming up where we'll be able to see how it just kind of goes up and down for where the surface of the bedrock is. And now this is what we got after when the report was sent out, and it had the 4 profile lines on it, but now it gives us the depths to where some of the where the shale and the limestone and the dolomite are. And over here, I know it's hard to see on the chart, but the orange and yellows, and that's what you're seeing a lot of right in through here on these lines. Well, that was the slightly to moderately weathered or fractured solution limestone and shale. And the further to the right, the green is the limestone. And we are seeing some of that on here too. So this line right here, number 2, this profile line, on the next slide, I'm going to show what they call a slice. And that's going to be the view of what we're seeing underground. And that's the profile line 2. It'll intersect profile line 1, and it also intersects profile line 3. Okay, up here on the top, the X's are the shot locations. That was where, when they had the line run down for that profile line, that is where he would have hammered onto the metal plate, and then the reverberation comes back up and reads into the geophones. The geophones are your little upside down triangles up here on the line. So you can see that. Down here, 3 was the profile line that ran right in front of the door of the old Maggie's Market. It crossed over the tank pit that had where the tanks had been taken out. This was the area of the Maggie's Market building, and back here is that profile line 1 where it would cross, and that is to the north of the building. Now you can see down here this line, and that's the top of the bedrock from the resistivity data. So it's just kind of a nice up and down following through. You can see our silty clays, and then we're starting to get into some of the weathered shale or limestone. Here we got into limestone from what the resistivity of the seismic lines were showing us. And then we had some severely weathered limestone or shale. And this is towards the north end, which would be back behind the building. So we had top of rock, where you can see from the seismic refraction, pretty much runs just right the same with the interpretation of the bedrock from the resistivity data. So this kind of gave some projections of some possible pathways for water to flow. And you can see by the arrows what they're thinking. Pretty much it was going to follow the top of the shale and the dolomite. So with all the geophysics interpretation, we had miscellaneous metallic debris that may be present in the shallow subsurface on the western side of the building, indication of undulating bedrock surface between 4 to 18 feet, and that was when the line, the undulating, just kind of rolling up and down. It's a real smooth surface between the bedrock and the silty clays. And then the topographic high of the bedrock surface is in the southern portion of the site, which is the front of the building, which is also where they took the tanks out. And that made sense that if that was the highest bedrock surface in the southern portion, that was why they had to hammer down 2.5 feet through the bedrock to get the tanks to be able to set them in to the tank pit. So the potential preferential groundwater contaminant mass pathways exit at depth in the vicinity of the former tank pit. So we knew we were already into the shale at that point, and we've got a real Vissel shale out there, so it has a lot of fractures. So we were able to get a good idea of where we stood on the subsurface, so we could make the next decision, and that was where to place the bedrock wells, and then we would have to have them drilled. So the drilling took place January 9th of 2020. So we had a year, a little more than a year from when we had the original surface geophysics conducted until we got into January 9th of 2020. They came out and the overburden was drilled through to bedrock, and a 6-inch PVC outer casing was installed And this had to set over the weekend because you have to make sure that that outer casing is good and secured, because once you bring in the air rotary rig and they start drilling, you don't want your outer casing to pop out. It has to be in place so there's nothing falling into the hole when you are doing borehole geophysics. Later, on the 13th of January, they brought the air rotary rigs in and drilled the bedrock, and those were advanced to 25 feet below ground surface. So the ones you're seeing, the Monitoring Well 3 location, that was on the northwest corner of the property, and Monitoring Well 5, the road is right up where my cursor is, at the front of the building. So we had a real narrow strip to work in through here, and from the surface geophysics, we knew that there were some possibility of some buried metal items in the area, so we had to be careful where we selected for them to drill. So right there, they're getting drilling so they can put in the outer casing and get that set. So borehole geophysics. We used 4 methods for this investigation. And the first one was the 3-arm caliper, and that establishes diameter changes along the borehole profile. And it establishes the locations of fracture zones that can be interpreted. And we're going to see some real good examples on some of these upcoming boring logs on the readings. It was really interesting. Without the borehole geophysics, we just would not have gotten any of this information. So it was such a huge plus. Next was the natural gamma, and that uses the natural gamma probe to provide information about the geologic layers. Clay minerals are the most commonly observed natural gamma emitters, and those are on a count per minute. And you'll be able to see on the logs coming up that when we have more clay in the subsurface, you're going to see the line go to the right, and then when you get in towards the limestone, then that line is going to go back further to the left because the limestone's not going to emit. The clay, the most natural gamma ray emissions are usually caused by minerals containing potassium, uranium, and or thorium, and the clay minerals, which contain the radioactive isotope potassium-40, are generally the most commonly observed natural gamma emitters. So this is really going to be evident when we look at the boring logs here shortly. The next 2 of the 4 borehole geophysics we used were the acoustical televiewer, which is used to image the bedrock fractures within the hole and is used when you have water in the hole. And the optical televiewer provide detail, oriented structure, and geologic information for the dry section of each borehole. It kind of complements the acoustical televiewer, and Chris had shown a slide that pertained to some of the televiewers, but the images, not the images, I'm sorry, the instruments, we had all 4. There's one down the hole right now, and here's the other 3. The 3-arm caliper is lowered all the way to the bottom and then is brought up So with all the instruments, it's usually about a consistent 5 foot a minute is what the pulley they have set up for it to either be lowered at the same rate, or if the instrument has to come up from the bottom. And the gentleman that was doing the downhole borehole geophysics has the computer and everything set up in the back of his vehicle, and you could watch, and to me it was very interesting. I had not had a lot of experience with the geophysics, especially with the downhole, so to see fractures in live time come up on the screen from the different instruments, from where the 3-arm caliper and the acoustic televiewer, what you could see. I just thought it was pretty amazing technology. So we are going to now look and see what.
And Vicki, this is Drew. Sorry to interrupt. Just wanted to give you a quick time check. 5 minutes. Back to you. Thanks.
Okay, thanks. We're going to look real quick at the geophysical of the bore logs, and the top. This was a little bit of a green, and here is tells you how the subsurface down to the bedrock just kind of up and down like a roller coaster. This is on the the west side of the building, 1, 2, and 3. 4 was at the northeast corner. 5 was the southeast corner. It was the one that was back up. This one here I picked out, and we're going to look a little closer at monitoring well 3. And like I was saying before, the blue line and the red line. So the blue line was the 3-arm caliper. As they were reading this up, the borehole diameter is approximately 6 inches wide. So it pretty much stayed true. You can get a little bit here, and that was where we were near an open fracture plane. So one of those arms kind of got over a little bit into that fracture. And then as it was coming up, it went all the way off their screen, which the maximum caliper reading ended up being 8.3. So we knew we had a void in there, and we were at that point, through the red line, we could tell we were into the dolomite limestone. And then right up here, we were in the black fissile shale, and you were picking up more of a contact with the clay. So that was emitting more, so you were able to see that. But right here, that was, I thought was pretty neat to get to see just how precise these instruments are. So the next slide, this is still monitoring well 3, but I blew it up a little bit more so you could see from the acoustic televiewer, you could see in through here that we got into some areas at 17 feet. We started to see some sheen on the water, and we had an open fracture plane right in through here. And this was at 1970. You can see this lighter color, and that was a vuggy area, which is small cavities in a rock or a vein, usually lined with crystals. And so we were down into the dolomite limestone. As we're coming down, we can see some of these lines, and we were able to pick up another open fracture down here, and we were able to see sheen on the computer screen as this was going on, which I just thought was pretty fascinating. So with all the information from the borehole, that was generated from everything that was given, we had a clear picture of how to design the bedrock monitoring wells to maximize the sampling of water-bearing fractures and smear zones that were encountered in the investigation. So on January 14th, that was the 13th and 14th, was the drilling, and then the downhole geophysics. And then we came back in about another week after they got us a rough draft of the borehole logs, and we were able to, at that point, decide where we were going to screen the 5 monitoring wells. And we now have a directive for 4 groundwater sampling events to be held, 1 each corner. That way we'll hit each seasonal variation, which can be sometimes a real difference in Kentucky on dry and wet seasons, to see if this is going to move them through any of the product through these fractures. So overall, it was, I think, a great success. I had never done a project like this. I'm always open to trying something new. So I was just real pleased with how this is turning out, and hopefully we'll be able to get this process through, get all of our groundwater data, and then get the site closed out for no further action eventually. That's our goal for all these sites that we have in Kentucky that we're trying to clean up. So at this point, I would like the acknowledgement. Shield Environmental was the contractor on site. Our drillers were from the Strata Group, and all of the geophysics was done by Mundell Associates out of Indianapolis. And I'd like to thank all of them for the great work they did. And a big thank you to all my colleagues here at the UST branch. A lot of support sometimes. And I'm the first one to admit, when I don't know something, I go find somebody. And so some of my colleagues would be, of course, they're all working from home, get phone calls or text messages. I'd have questions, and everybody was always a big help. A lot of support from everybody, especially branch manager Don Basie and Ed Winters up in the assistant director's branch. Really appreciated all their help that they gave me. So that's my presentation.
All right. Well, thank you so much, Vicki Voisard with Kentucky DEP. We really appreciate your presentation. Friendly reminder to the audience, again, whether questions are for Chris, Vicki, or our next speaker coming up, please fire them away to me at any time. You don't have to wait until the panel Q&A starts. We'll get a good log of questions going, and that way we've got some good ones to throw out there to our panelists. So please send your questions in as they come. And thanks again, Vicki. And with that, it's my pleasure to introduce our final speaker, Bill Brab with AST Environmental.
Thank you, Drew. Can you hear me okay?
You can. Take it away, sir.
Excellent. Yeah, thank you, everybody, for sticking around. I appreciate Chris and Vicki for leading up with the 2 presentations prior to mine here. And I'm going to take what both of them have talked to a little bit of a step further and take it to the position of the remediation contractor, which is what AST Environmental is, and looking at taking this high density qualitative characterization and surgical high pressure in-situ injection method to the field. So before we begin, a couple of comments, and I think Chris covered this quite well in the ITRC discussion, is looking at, most of the situations where remediation chemistries fail, looking at why they work so well in a beaker or column study, but moving into the field, we do have these situations where we don't have a lot of control. And looking at the heterogeneity versus the homogeneity and isotropy. But the other part of that is looking at inaccurate loadings and dosings of reagent. The contaminant mass distribution can be quite complex, and at scales which are reflective of the heterogeneity of the lithology. And in a lot of situations in the work that I look at when evaluating facilities is the lack of consideration for the soil mass distribution contribution to the total contaminant demand. And this is typically underestimated or not understood at all. And the other part of that is contact with the contaminant itself. We all know that getting the reagent in contact with the contaminant is critical to success. And being able to assess distribution to confirm how you actually implement the material within the subsurface is important as well. So leading up on the front end here, with the ITRC documents that were referenced earlier, this process is illustrated quite well here as well. Remediation Products Incorporated developed this flow path many years ago as a roadmap to success. It's just generically called the approach in our inner circle here at AST and RPI. Initial review looking at the conceptual site model that's available at the moment of remediation assessment. Typically during that phase, you're going to identify data gaps and components that need to be refined as far as how we understand what's going on at a facility. And this kicks into play the next step in the process, which is the remedial design, RDC for short, but the remedial design characterization and investigation. This is what's used to refine the conceptual model, come back to the table once we have more information, and reevaluate a preliminary design, which is typically, the preliminary design is typically and historically fairly conservative because a lot of assumptions go into it. But that redesign is tailored more for the current site model, and then moving forward with some sort of implementation of a remedial objective and plan. And then, of course, you have your verification using post-performance monitoring. So I'm going to interchangeably use high-density qualitative characterization with the RDC. And what I really want everybody to pay attention to here is the word qualitative. And this is important later. It's qualitative information on the front end usually ends up looking at the information available that we have on what Drew talked about with our desk side or computer top geology and information about the site, looking at the historical information that we have available to us. And so this is your typical site information, looking at the geology. How old is the data? Is it recent or is it fairly dated? Groundwater levels, groundwater flow direction, groundwater concentrations, geochemistry itself, soil concentrations, and any prior remedial efforts that have been applied and attempted. But moving forward now, we want to talk about what we really want now is to change that cue from qualitative to quantitative. And what we really want to know here, and taking this RDC to the next level, is to have a detailed understanding of the vertical and horizontal distribution of total mass within the system itself. And using this remedial design characterization that Drew has talked about and that I'm going to elaborate on as well and build upon, is the critical step to fine-tuning the CSM. Drew hit on it really hard. The CSM is critical to success on any remediation project that you have. And taking this RDC to the field, we're going to be looking at dense vertical soil profiles, typically on the order of every 1 to 2 feet. Looking at using hydropunch or nested temp wells to look at any sort of horizontal and vertical variation in the distribution of the groundwater impacts. If your state permits it, leaving these temporary locations in ground can also be used during any sort of assessment during the implementation phase of a remediation project. We also can use the direct imaging high resolution site characterization tools like HBT or UBOST to assist with this RDC effort. We can also take the opportunity to look at the actual aquifer characteristics and try and determine a mass discharge calculation by getting a site-specific K that can vary both vertically and horizontally depending on what unit you're looking at. These are quite valuable for looking at barrier situations where you're actually looking at capturing mass as it's moving through a cross-sectional area of treatment. And then getting into competent bedrock, we've talked about geophysics as part of the upfront characterization, but then also using packers for the purpose of actually assessing features that are identified during the upfront characterization work. And again, I want to stress heavily the word quantitative here. One of the other key components that's extremely important for a successful RDC and update to the CSM is quantification of total contaminant mass. And one of the values of RPI is a in-house laboratory that allows for free analytical service on any remediation project that we're involved in. And that allows us to not be hamstrung by the cost of a commercial laboratory analysis that is required for getting this data. This is non-compliance data, but it is used for remedial design purposes, and several states, including Kentucky and Tennessee, have accepted the data as valid for the purpose of evaluating. But for your standard compliance and decision making on closing or not closing, you still want to run a certain subset of that data through a commercial laboratory that has the required certifications for the respective programs that you're involved with. RPI's methods that are offered are volatiles using GCMS 8260 B and C, looking at total fraction, TDPH. Here it's identified as GROW, but also looking at TPH DRO for diesel sites. Also looking at anions and VFAs and groundwater chemistry using ion chromatography, method 300.1, excuse me. And then also looking at dissolved gases using method RSK 175. And this is quite handy in looking at byproducts coming off of any sort of biological or abiotic process that may be involved. And so I harped earlier again on this lack of soil data, specifically saturated soil data. A lot of sampling protocols require that once you encounter first water, you stop soil sampling. Also, in a lot of instances, the risk and contribution of soil mass is underestimated and disregarded. But we can see here with a simple schematic, and this is real data. All the data I'm going to show you here isn't made up. It's all from real sites. And what I want to show here, a lot of text, but essentially looking at the red bar in the center is a 20-foot well screen, and looking at a composite groundwater concentration of 54 milligram per liter benzene within the well. I have the water table depicted here at roughly 32 feet below grade, and the dark blue line that squiggles from the left of the page to the right of the page is a high density soil boring that was advanced next to this well. And what we see here is that if we were to stop sampling at the water table, you would have found a high contaminant hit of, roughly call it 8 to 9 ppm in soil. But directly below the water table, this could be due to seasonal variation or significant hydraulic head from the contaminant release. We actually have contamination that's made its way below the water table. And we have an extremely high hit of benzene in soil at 36 feet of 90 ppm. And just backing into your simple mass calculation based on the media that you're working with, if we look at just the groundwater across a 20-foot thick zone, you're only looking at 454 milligrams per cubic foot. But if you normalize the concentration for the soil concentration at that one specific interval of 36 feet, you have nearly 10 times the amount of contaminant mass present in that one specific zone. So if we were to go in with a remedial plan targeting strictly that 54 milligram per liter in groundwater, and that using that actual mass per unit volume contaminant loading, we would be underdosing across the entire vertical interval and missing a very large chunk of mass at a very narrow surgical interval that we would need to address later on down the line that would be further contributing dissolved mass to that monitoring well. looking at some more diesel data here specifically, and again, busy slide here, don't want to get too inundated in this, but what I want to show here is the intense variability of the data that you can see respective of, above the groundwater high, within the groundwater average, but noting some significant hits well below the groundwater table, even at its lowest point during the seasonal variability at the facility. So again, continuing through the entire borehole and getting this data would be invaluable in aiding us with ensuring that we're looking at the picture of the site with the best resolution that we have available to us. and I would be not wanting to miss the use of the high resolution screening tools that we have available for us now for helping us to make decisions for where to sample and how far out we need to step. And I just want to caution here that we have to be careful with this as well, that trying to correlate the response data from these high res tools, specifically looking at UVOST here. Again, it's a great tool for helping us to guide a sampling plan, but when I look at the actual analytical data that's collected in hindsight of that, trying to correlate to the specific percent RE that is displayed from the direct imaging tool during screening can be quite varied, and I've got several slides here to show this. And so what I really want everybody to look at here just really quickly is the percent RE for both of these logs is roughly 2x difference. But if we look at the benzene concentration, for instance, the higher percent RE actually has the lower benzene concentration compared to the adjacent one with 0.5% RE, order of magnitude difference on the benzene. Similarly, on the reciprocal of that, looking at the total mass fraction, TPH grow, you can see a similar strange detection as far as the total mass present. The percent RE on the left has a fairly low TPH grow concentration, but the lower detection on the right has yet again another order of magnitude increase on the total mass present within that borehole. Another instance here that's interesting to note too is similar numbers in percent RE, and seeing that the benzene concentrations, excuse me, here are similar in concentration level, but again, looking at the total picture of what's present within the subsurface, that total fraction hydrocarbon that's present within these two boreholes at the facility are yet again an order of magnitude apart from one another, and can show that there is quite a bit of variability in the data that you get from these boreholes at specific sites. And finally, just one more level of this as well, of the UVOS data with in side-by-side comparison, looking at diesel here in this instant. So just the full plot on the left, expansion of the plot to the right, and then data table of lab analytical lined up to this particular location as well on the right-hand side with respect to its rough location on the vertical plot on the expanded image here. And just another takeaway here, your higher plots on the upper part of the image and the yellowish green plots show respective DRO concentrations of around 3,470 ppm on one of the highest DRO concentrations, but down at the lower interval of 26 feet, where we have the lower blue concentration, or the blue response on the data, shows the highest concentration towards the bottom of the borehole. And again, this is just important to note that we want to use all of our tools to our advantage. This UVOS tool is telling us there's something there, but what's really critical is now we have to go in. This is qualitative data. Now we have to go in and get the quantitative data that actually tells us how to design a treatment amendment and remediation plan accordingly on a contaminant demand basis. And so some considerations for bedrock. We've talked about overburden so far, but the data caps and holes in a preliminary CSM on a bedrock site typically target monitoring wells with long well screens that span an extended heterogeneous mix. Cased wells can't be used for a whole lot of anything for like downhole geophysics or slurry injection. They're essentially ambient water level monitoring and composite groundwater sampling from an extended water column. There's no discrete groundwater characterization data present from these cased wells. And a lot of times there's no matrix characterization. So going back to this idea of looking at the contribution of the soil mass on an overburden scenario, looking at the matrix characterization, we don't look at if there's any contribution of any sorbed mass on any sort of contaminant that's actually adhered to any rock surface that has a potential flow zone. Are there also any soil-filled permeable zones? And then just an extension of that, the lithology is typically logged from chips expelled during an air rotary installation. These are just blown in, and it's like trying to log soil coming off of auger cuttings and overburden. What we really need here is a rock core. And so taking a preliminary design on a bedrock basis, the estimates are based on, thick saturated profiles with no indication of a high concentration versus a low concentration interval within that extended vertical borehole. We're typically using published or estimated values from for porosity and hydraulic gradient, and we're assuming a homogeneous stratigraphy and only looking at groundwater mass. So we don't have the whole picture in a bedrock scenario in this particular instance. So a lot of these tools have been talked about earlier, so I'm just going to run through these fairly quick. On a bedrock RDC, we're going to want to use surface geophysics using our methods that we like are 2D ERI and induced potential in parallel with a multi-channel assessment of surface waves, which is basically a seismic method like Vicki talked about. For the characterization part and moving into potential use of injection wells, we want open boreholes with surface casing. And then while we're drilling those holes, we want to be able to take rock cores so that we can actually look at logging the actual characteristics of the bedrock media itself and actually the potential to sample some of that matrix if we see the need to. Then coming back and looking at these open boreholes, looking at using some of these downhole wireline geophysical methods. Again, Drew and Vicki talked about this quite extensively. Caliper, acoustical optical televiewer, and using downhole camera to look at real-time depth and orientation of features in the borehole. And then the next part that I'm going to go into that is taking that a step further from earlier discussion is using groundwater characterization methods that involve using pumping tests, discrete interval analytical sampling, and looking at the responses of transducers in the surrounding well network, as well as within the borehole itself that we're pulling from, to look at the actual hydraulic characteristics within the surrounding aquifer matrix. So just some quick slides of the surface geophysical methods in parallel. The upper image here is showing the 2D ERI. The middle image is induced potential. And then the bottom image is the MASW, which is the seismic method. And so just to build upon maybe something that Vicki talked about earlier, the two-dimensional ERIs were inducing a current onto the formation and reading the resistance of the media that it's going into. The induced potential is then turning off of that current and seeing what the capacitance and the bleed out is of that formation as the capacitance is discharged from the formation. And then using the seismic data below helps us to refine what that data is telling us and how to map that bedrock surface so we have a better indication of where the overburden and where the competent geology below it intersect one another. I mentioned rock cores earlier doing the drilling process itself, and we can clearly see standing by a pile of chips versus looking at these nice logs, we can see some dipping beds with the far right photo shows precipitate on a bedding plane that was intersected by this rock core. So we're actually able to see the characteristics of the log of the rock itself as we're pulling it out of the hole, and we're actually able to characterize the nature of that material and have a better indication of what this material really looks like in situ and how we're going to be working with it. Using the downhole geophysical methods, here we're looking at caliper and fluid temperature and conductivity methods. These are two boreholes on a particular site separated about 100 feet apart. Elevation on the depths have not been, or the depths have not been corrected for elevation, but the two features you see on the optical televiewer image that we have here are essentially on the same elevation topographic line and are connected and fairly continuous across the site. So we're able to use this imagery and this information to show us where the high flow versus the low flow pathways are within a borehole. And then finally about this, the other interesting part that we want to really drive home is the characterization of the borehole itself. We do have some pretty cool tools at our disposal at AST that have been developed over the years. We use discrete interval straddle packers as a method for not only assessing the aquifer for characterization purposes, but we have another packer that's twin to it that's used for injection. The far right image on this particular slide, you can see the traditional off-the-shelf straddle packer assemblage. The interval between the inflated packers is somewhere around 5 feet in length. So you're looking at a fairly large section of borehole. And if you don't have the ability to isolate narrower zones, you could probably be getting, yet again, a situation of the long screened intervals in a well where you're looking at a composite of multiple intervals together. Ray showing the 18-inch interval with his hand on the 2 inflated elements. But the other part that's really interesting about this packer, the straddle packer that we have, is the ability to pump from that discrete interval with the Grundfos ready flow 2 pump. That's a variable speed pump. And we also have pressure transducers within the borehole itself to look at vertical connectivity within the borehole that we're pumping from. But then we also deploy transducers in the surrounding well network to look at the response during pumping from the adjacent wells that are proximal to the location we're drawing water from. And so looking at, as part of that aquifer pumping and assessment, we also do discrete interval sampling. And again, going back to the benefits of the RPI laboratory, we have several methods and the ability to send as many samples as we want without any issues of scrutiny for a cost. These are all just part of the package. And what we're seeing here is looking down the borehole. So the y-axis on the left is looking depth below ground surface, going from top down on the left-hand side. The red graph is TVPH, looking at that total mass fraction hydrocarbon, and then benzene is in blue. And then the dotted lines on the page here are just showing respective individual discrete intervals that we pulled from. And you can see the separation between some of these dashed lines are quite narrow. So if you had that traditional off-the-shelf packer, you wouldn't be able to really isolate some of these locations and look at how the data changes within a very short distance within the borehole. And you can see just the yellow line being 28 and the underlying line 32 feet. You do have quite a bit of variability and a significant change in groundwater concentration with a very short distance and depth. Looking at some of the geophysical data from earlier as well. Very busy slides right here, but just in short, the far left geophysical plot here is a monitoring well adjacent to a deeper monitoring well, which are the 2 plots on the right-hand side here. Historically, this is a site with TCE contamination, and historically, this feature at roughly, if you can see my mouse, at roughly 21 feet was identified in the geophysics, and the consultant on the site decided to do some permanganate injections in a upgradient well and use extraction methods to draw and induce flow to that high flow feature within this deeper well. And on the right-hand side here in the fluid temperature and conductivity column is analytical data from the discrete interval sampling that we performed in this well. And you can see that the concentration at this high flow zone cleaned up quite well to getting about 54.8 ppb in groundwater of TCE. But because there hadn't been any discrete interval sampling, they're still getting, if you were to sample this borehole in composite, you would see that you're in the ppm level of TCE. And so it's not understood, initially wasn't understood what was going on here. And again, looking at the adjacent borehole here on the far left, we can see that by mapping and looking specifically at the discrete interval at that high flow zone, we have a different varying concentration still elevated in the monitoring well, that the permanganate itself had not gone very far within that treatment zone. It had mainly just followed the direct flow path into that well that was being drawn from. So this site here has to have some more remediation done, and it has to be attacked in such a way that it's surgical and more precise method now that the picture is a little clearer as to what's going on here. Looking again at some other data, this is looking at benzene data at a different site. And again, on the far left-hand side, you can see how close the individual permeable zones that we were able to draw samples out of are quite close together. And again, with a traditional off-the-shelf packer, you wouldn't be able to really isolate these. But looking at the individual well benzene concentrations, what's interesting to note here is that the concentration is fairly consistent throughout the borehole. This isn't uncommon to see. But what we found that was really interesting during the discrete interval pumping and drawing water from the site was that during the pumping, two of the intervals, 42.5 feet, 43.5 feet, actually started pulling napple out of those specific discrete intervals. And napple had never really been encountered or seen in the wells at the site. But when you isolate and you're actually drawing from a single point within the borehole, we actually saw that this material was coming out and showing us where the high mass zones were within that respective borehole, and definitely changes the remedial approach and the method that we're going to attack those specific intervals going back for the actual implementation.
Bill,
so now
just want to give you a quick 5-minute check. Go ahead, carry on. Thanks.
Great, thank you. So getting into some slurry best practices, looking at proper installation methods for slurry. The bulk of our work that we do is through slurry injection. This is placing a material within the formation to become part of the aquifer matrix. These temporary bore points are done by a top-down method, and the path of least resistance here is going in the horizontal. These are all dedicated temporary points. And the key to installing a slurry within the formation in this manner, well, in general, is using high flow rate and relatively small injection volumes across the site. Looking at the actual injection tips used, geometry and configuration matter. There's not just one off-the-shelf tip that we use. The left image here shows some of the variability of the different injection tips that we use with our systems and overburden. And on the far right, we have the straddle packer again, showing the isolated interval. The yellow shroud is to protect the bore wall. So we're putting a lot of energy into the formation with the injection fluid going in. And we don't want that material jetting off into the formation and cutting and dislodging material. The packer is quite expensive, so we want to maintain the bore integrity, but we still want to be able to take advantage of that volumetric flow that's coming out of that packer. And just to get in, again, talking about proper methods of installation, low flow, low pressure injection. The fantasy here on the left shows even distribution across the entire vertical interval, whereas the reality is that you really don't know where it's going. The low pressure injection doesn't account for low K zones. There's preferential flow based on just where it wants to go. And then using injection wells, dedicated injection wells, you typically have limited coverage. Using the pressure signature on the high pressure injection tells you what kind of geology you're in. Really quickly on the left, looking at a fine grained sediment like a clay or a silt, you've got a buildup of pressure to a fracture pressure, and then lower pressure as it's sustained throughout time until the end of injection is the propagation, and you develop seams and pathways through the soil. Cross-sectional area here shown of an example soil boring advanced in the area of a completed injection. Far right, looking at coarse grained sediments like a sand, looking at trying to achieve a buildup to a peak fluidization pressure. So trying to actually cause localized mixing and turning of the soil in the area to blend and feather that material into the formation. And some example logs of showing that, the top image showing more seams, or the top boring showing more of seams, and then the bottom imaging showing more consistent color variation across that borehole, showing more of the feathering instance that we're looking for. Injection grids, they're tighter and more dense than most people expect. Our typical injection grid is either 5 foot or 7 foot triangular grid spacing. And this is method to the madness. It's shown to be quite successful on increasing the probability of intersecting with the contamination in the subsurface. The grids are oriented perpendicular to groundwater flow, and as you can see from the IMP locations, these are temporary sampling points that can be used for distribution verification during the actual injection itself. Permeable reactive barriers are another method for in-situ treatment. If you're using an injection approach, it's going to be multiple tightly spaced rows, looking at a minimum of 3 to 4 rows for a barrier. being able to trench in is the best way to get it in, because we can actually see the material go in and make sure it's actually being blended in evenly across the interval. And it's great for shallow applications, but depth limitations are typically a problem. And then because we're looking at discharge across a cross-sectional area, we can install injection wells for the purpose of adding soluble amendments for future delivery. So looking at the addition of TEAs or something else that may be needed to sustain, for instance, a biological degradation pathway. Again, looking at the bedrock stuff here, we've talked about that. Just another picture of the packer inflated versus uninflated. The other half of that equation is a significant pump with quite a impressive capability. The pump is coupled to the PTO of a Kenworth 12-cylinder, or excuse me, a Caterpillar 12-cylinder diesel motor, 8-speed transmission, and depending on the gear of the transmission and the RPM of the motor, you can get quite an interesting output of pressures and flow rates available at your disposal. Can't go into detail of why this is important in this presentation, but I'll point you in a good direction at the end of the presentation here of why that's important. And then let's looking at an overburden injection tip using this pump, showing the different flow rates. So 20 GPM top left, 60 GPM top right, 120 GPM and 250 GPM. So just a visual comparison of the respective energies from these different flow rates coming from this significant unit that we have on our fleet. And I would also be missing the game here if I wasn't mentioning some powerful products that we utilize that make this process complete when we actually get to the remediation side. So mentioned RPI, Remediation Products Incorporated earlier, and their stellar line of products, Trap and Treat, which is on the market for you to consider. Using activated carbon for sorbing contaminants. This is the trap method. So decreasing groundwater mass and flux immediately disrupts the equilibrium between dissolved and sorbed phase. This is key to removing source mass remediation. And the carbon allows for concentration of mass on the carbon structure, bringing it in contact with the degradation pathway, and this accelerates the degradation rate substantially. And then the degradation mechanism is the treat part of that, and we have bioremediation using aerobic or anaerobic with the BOSS 200 for petroleum hydrocarbons, or abiotic chemical reduction oxidation using metallic iron in the BOSS 100. Two products here. BOSS 100 is granular carbon impregnated with iron, primarily used for chlorinated solvents. BOSS 200, primarily used for the treating petroleum hydrocarbons. This is powdered activated carbon mixed with turbine electron acceptors, micro and macronutrients, and a consortium of facultative bacteria, somewhere on the order of about 37 microbes at this point that are both aerobic and anaerobic in nature. And then an improvement upon the BOSS 100, which is using, again, the activated carbon with metallic iron, but adding, in this case here, a complex carbohydrate in the form of a food-grade starch, a couple microbes, one for being able to degrade the contaminants of concern, but then a second set of microbes to break down the carbohydrate, make it into simple sugars for more availability within the system for the bio. And then this is developed for situations where high concentration is present in the form of DNAPL, where the amount of iron is insufficient to limit the long-term performance. And I'll finish there, just noting that I covered a lot of material here that I couldn't go into a lot of detail on just due to the time constraints of the presentation. But I want to invite everybody. We did a extended webinar series back in the spring that was quite productive, enjoyable, and successful. I've noted the website here. If you've downloaded the slide deck, you can click this link and go see everything that we talked about regarding carbon, permeable active barriers, bedrock overburden, numerous topics that are available at your disposal at this web link here. And obviously, don't hesitate to reach out to me directly if you have specific questions to my email address here, and I would be more than happy to speak with you in detail. Thank you, everyone. Back to Drew.
Excellent. Thanks so much, Bill. Bill Brab with AST Environmental. I'd like to go ahead and get things started with the time we have left with our Q&A. So did get a few good questions for our speakers here. So bear with me as I kind of navigate through things. I'm going to go ahead and just kind of put up that placeholder slide for now as I kind of click through these questions here. But again, you know, we've got time to keep fielding these. So if you have a question you've been sitting on, or maybe one that just came up there toward the end as Bill was wrapping, please use that questions feature and send something my way, and then we'll work to get to it. And if not, maybe I can link you up with the appropriate panelist or the entire panel afterwards if we can't get to your speaker. So I'm going to go ahead with our first question. I'll encourage the panel too, even if the question is not directed to you, if you want to piggyback on what one of your co-panelists is saying, or if you have value to add to the question. I think we can do this, you know, somewhat informally, like a real panel would be in person. So let's see the first question I have here. So first one for Chris. So Chris, this person's saying, states have limited funds to administer their programs. So do you have an average cost to conduct the bench and pilot scale tests?
I do not. I don't have a. Generally, we don't do it. Usually, it's a consultant that does the bench or pilot test study. So I'm sorry about that. I don't have an answer for that.
No worries. Thanks for the question. So jumping over to Vicki. The question is, you used, it was midway through your presentation, you talked about the seismic refraction profiling process. Could you just reiterate or say more about why that method was used? You made a distinction between that process versus another.
Oh, between refraction and reflection, we went with the refraction because we were not going. We knew we were only going to put the boreholes down to 25 feet into the bedrock. If we were going to a depth of 80 to 100 feet, that's when you would want to use the reflection. And that's why we went with the refraction, just because we were not going that deep.
Great, thank you. The next question is for you, Bill. The question is, if you are analyzing soil data from below the water table, isn't that processed by the lab and reported as a water result?
No, it is not reported as a water result. It's still using the standard GCMS, and I believe they do an extraction method for that. So it's still considered a soil analysis.
Great, thank you for the clarification. So this question might actually be more for NUIPIC than Chris, but the question related to all of the links to the ITRC documents and resources, those hyperlinks and Chris's presentation. Yes, I think I mentioned earlier on, NUIPIC will be, along with the live webinar recording, the video and the audio, will be posting all the panelist slides, the whole slide deck from today to our website. So I think I've got a link to that at the end here. But those hyperlinks within Chris's presentation that will link you to the ITRC resources will be accessible on our website. So yes, a long way of saying yes to that question. Right, let me see. I had another one here for Bill. The question for Mr. Brab: what is the maximum depth your injection technology can work at?
Good question. We're typically only limited by the drilling technique and the drilling availability. If you want to reference again the web link at the end of my presentation, there is a discussion of a recent PRB that we implemented on a DoD site in South Carolina, where we used the pre-drill method and actually advanced tooling and injected at a depth, I believe the max depth was 180 feet below grade in overburden sediments. The deepest bedrock, the actual consolidated material we've been in so far, I believe is around 120 feet. But again, this is simply limited by borehole accessibility, not by pump or pump capacity or properties of the material being injected.
thank you. So next question's for back to you, Vicki. Will the bedrock wells and the GPR profile help determine if the Mitchell Spring is impacted or will be impacted? And the person goes on further. It seemed that Pinnacle to the north might be protective to the spring. Is that what you're thinking? Is that what you feel?
We got analysis back from the first round of groundwater sampling, and one of the most important things was at that time to determine groundwater flow. We are, as of the first sampling event, groundwater flow is going to the west and southwest. We are not headed towards the spring. So I was just really glad to see the data on that. But of course, with all the groundwater data, we will, every time we do a sampling event, we are sampling Mitchell Springs just to be doubly sure that nothing is going into that creek and coming up through the spring.
Great, thank you. So this next one, I'm going to just throw it out to the panel to see if you all have feedback on it. It's not directed to a specific speaker, so maybe it's a panel question. The question is there research comparing effectiveness of injection under pressure versus passive only?
I'm not sure what the reference to passive is. Are they referring to? I'd like to, I guess, extend the question further to clarify if they're talking about inducing under pressure that's beyond soil failure versus low flow, low pressure in a situation like I described in mine.
So if that person wants to send kind of a follow-up clarification, they say low flow, low pressure. So I'll give it a minute. If that person wants to just reframe the entire thing as maybe a rephrased question, that might help. And I'll just kind of bump back to the attendees again. Still got a couple of valuable minutes here with our panel. And I'll also open up to the panel if you all had questions for each other or wanted one another to expound on something that was mentioned. Feel free to kind of bring something up now. We'll wait for that person to maybe send in a clarification. At this point, it looks like I'm running low on questions. So last minute or two to get one in for our panel on the live webinar here. So I'll hang tight and hope another question comes in.
I'll just add that to that question about the links, ITRC web.org. That's the main page for ITRC, and from there you'll get the training, the next webinar. You'll be able to sign up for the next webinar that's being held. You'll see the documents, plethora of documents, and then there's also a search feature under documents to see what subheading you'd be interested in. So very, very rich website to it. Anyway, for the verbal, to give it verbally, itrcweb.org.
Great, thanks, Chris. So I'm gonna give it another minute here. If anyone's sitting on a question or co-panelists want to put something out there before we wrap things up.
I'll just admit, Bill, that I always thought the RE percentage on the LIF on the UBOST, I always correlated that to being either mobile or stationary free product. So good to get that straightened out. Done a lot of LIF, done a lot of UBOST and MIPS and LIF investigations at petroleum sites.
Yeah, it's a valuable tool, and you know, I've been using it recently for assisting with the actual sampling plan, and doing that in a relatively short period. You know, the historical hurdles that we've run into is that the high-res tools are used on a standalone basis, and then there's a significant lag between the use of the high-res tools and any sort of sampling for quantification on a remedial design purpose. And so some of the recent improvements with the way things are being approved and directed is to do them in parallel, to do the ITRC, evaluate the data in real time to figure out where to go, and then come back in a relatively short period to get the actual confirmation data, so that the time to remediation is greatly reduced, and that benefits the responsible party and landowner immensely, as well as the reimbursement programs, the taxpayers as well, because it reduces that time that the project is in that evaluation period before moving into active remediation.
Excellent. Okay, thanks. I do want to get one more out there from the panel, or sorry, to the panel from the audience here. I think we've got just time for one more, so it might be tough to answer in this short time. If you all want to offer, 20, 30 seconds on a response. The question is, how do you deal with multiple aquifer zones and multiple contamination zones in a single site when injecting?
I'll volley that, and I think it depends. is the best short answer for that. Looking at, let's just pick, for instance, a military site where you've got a burn zone, or a burn area where you've got petroleum hydrocarbons, and in close conjunction with a tooling operation where maybe you have chlorinated solvents, or even, I've seen before where there's like an area where they have chlorobenzene and such associated with like portable toilets. You have to look at the distribution of it. You have to know the total contaminant mass present of each respective contaminant, and then looking at the demand is an important part, and compatibility of the reagents that you're looking at. Sometimes your demand for instance, the chlorinated solvent is so low, but the actual contaminant demand that's of significance is going to be your petroleum hydrocarbon, and so your remediation chemistry is going to be geared towards remediating the petroleum hydrocarbon, and maybe getting some sort of co-metabolic process that can resolve the secondary contaminant. Similarly, with your vertical variation, different zones within an aquifer, for instance, like two different water-bearing zones of differing matrix. Again, I'm going to point to that DoD project as a potential reference to look at that, where some of the aquifer chemistry was looked at to determine if you were in the right zone, but then also using our typical drilling tools and methodologies of different cased wells or isolated casing for the purpose of making sure your target zone is within the respective interval that you're trying to address, and you're not overlapping with another zone that's outside of your area of interest. So expansive answer there, but hopefully that covers and helps resolve that question.
Great. No, thanks, Bill. I think that brings us home right there. So just looking at the time, I think we've come to the end of today's webinar. I'd like to extend, again, a huge thank you to Chris, Vicki, and Bill for speaking today. Also want to thank NUIPIC's partners in the states, the tribes, EPA's Office of Underground Storage Tanks, and SWOMO for helping plan today's effort and the overall NTC webinar series. This webinar will be posted on the NUIPIC website. As I mentioned, you can find other resources there, other archived webinars.